really a pleasure to have you all back with us. We are continuing the Spring 2023 series, and we are honored today to have another member of the C2QA family from Yale University in Brookhaven, Kevin Smith, who's postdoc with his postdoc advisor, Stephen Gervin, who will do his formal introduction. Professor Gervin?
Hey, good afternoon. So it's a pleasure to introduce Kevin Smith. Kevin, as mentioned, is a C2QA postdoc who's actually employed at Brookhaven National Laboratory, but he's posted here in the Yale Quantum Institute, where he's been for nearly 2 years. Kevin got his PhD at the University of Washington, and in his time in C2QA, he's been thinking about how to create interesting and non-trivial quantum states of spins, and has done simulations of them, this new protocol that he's developed on the IBM Q systems. And that's what he's going to be talking to us about today. So welcome, Kevin.
Yeah, thanks. So most of the time when we think about implementing quantum algorithms on hardware, sort of the natural picture that comes to mind for me anyways, is we have some particular arrangement of qubits, maybe with some connectivity, and we apply local unitary gates to these qubits in some order and make measurements at the end. Okay, and so many quantum algorithms look something like this. And really the bread and butter here is figuring out how to implement your algorithm with local unitary gates. However, on the other hand, when we think about today's hardware, more and more we have access to a broader toolbox. You know, we don't just have local unitary gates, we have things like mid-circuit measurement, we have qubit reset, and even classical feed forward, where you're taking the results of measurement and feeding this into the very logic of what unitaries to apply next. And so at a very high level, what this talk is about is the following question. Are there tasks which we can perform more efficiently by leveraging this broader toolbox as opposed to just relying on local unitary gates? So taking advantage of these additional resources such as mid-circuit measurements and feed forward. And so more narrowly in this talk, I'm going to be focusing in on a recent paper by myself and Steve and our co-authors listed here, which this is really a story of state preparation in particular, and preparation of something known as the AKLT state. And what we show in this paper, and what I'll share with you today, is that this is an example of state preparation which we can drastically speed up by leveraging this broader toolbox, as opposed to just relying on local unitary gates. And furthermore, that this isn't just something of theoretical interest, but something we can really take advantage of in the NISQ-era. And I'll show this by sharing, as long as there's enough time, some experiments where we run this preparation on an IBM Quantum device. Okay, so that's the general plan for today. Here's the outline. I'm going to start by briefly reviewing the AKLT model and discuss what the AKLT state is, and why it's an interesting state to try to prepare. I'll then move into sort of the bulk of the talk, which is to describe this algorithm we've developed in order to prepare it. And I'll do this in two parts. I'm first going to explain how you can prepare the state without using these additional resources. And this will sort of form the backbone for how we can then speed up this procedure with these additional resources. And then as long as there's time, I'll also share these experiments where we actually run some of this on an IBM Quantum processor with the goal of showing that this measurement-assisted approach to preparation can really outperform its purely unitary counterpart. And then I'll conclude with some thoughts about how this connects with other work recently in the field. But first, as is the custom in these C2QA Quantum Thursdays talks, I was asked to briefly describe my trajectory to my current position. So as already mentioned, I'm a postdoc within C2QA at Brookhaven National Lab and seated at Yale University. And so my path has been a pretty straightforward one, to be honest, in that I did undergrad, then grad school and postdoc, sort of physics the entire time. However, what was maybe a little bit more winding was the path I took to end up in quantum computing and quantum information. So in undergrad, I had my first exposure to research. So I was at University of Massachusetts Amherst, where I did my bachelor's in physics and math. And my first research experience was I worked for a couple of years in actually an experimental biophysics lab. And so this is quite different from what I'm thinking about now, but basically the general idea of what I worked on was studying force generation in yeast cells during mitosis. So pretty different from the stuff I think about now, but was nonetheless, this was an extremely valuable experience in that it taught me sort of not only what research looks like, but also gave me a lot of useful skills. So I got a lot of coding practice, practice giving talks, and these sorts of skills. I think even if you're not thinking of going to grad school or you aren't sure, getting involved in research, I think, is really, really beneficial at the undergrad level for this reason. But another really useful thing was I also got to meet a lot of grad students and talk to them. And this was really when I first started to think about going to grad school, which I hadn't seriously considered before that. And the summer before applying for grad school, I was working as an intern at MIT Lincoln Labs. And in something sort of unrelated, it was like a data science project, more or less. But outside of my office, there was this bookshelf that sort of just had overflow books from the library, and you could take them home, and they were free. So I spent a lot of time that summer because I was in the stage of my career where I was just reading anything I could get my hands on and learning about lots of different topics and fields. I wasn't too focused on any one thing. So I spent a lot of time picking through this bookshelf and sort of starting a collection of books. And one day I stumbled across a copy of Quantum Computation and Quantum Information by Nielsen and Schwang. So this is a book which obviously for anyone in quantum computing, this doesn't really need any introduction, but at that point I really had no exposure to quantum computing and I wasn't quite sure what this book was. So it was pretty fortuitous, and there was no one at the time, this is not the case now, but at UMass Amherst, there wasn't really anyone thinking about quantum computing. So anyways, I spent much of that summer actually during my lunch breaks reading this book and really started to fall in love with it, and started to have my sights set on trying to do my PhD research in quantum computation. So I ended up going to University of Washington to get a PhD in physics. And for about my first year and some change out there, I worked in an experimental trapped ion quantum computing group. And it was sort of after that year, particularly after my first full summer working every day in that lab, that I started to question whether I wanted to do experimental research and wasn't, I was starting to get more attracted to theoretical research. And this was because, a lot of my day-to-day was working on these optical tables, adjusting mirrors, and I don't know, I would walk away and get coffee and come back and everything was broken and not working how I left it. So this was an experience that I started to feel like, hey, maybe I want to focus on theory a little bit more and think about physics full time. And so, again, for anyone who's thinking about going to grad school, I think one piece of advice I have is not only to consider sort of big picture topics that get you interested, but also the day-to-day work, because you can be extremely interested in the big picture ideas, but if you don't like the day-to-day, then you won't enjoy doing the research. And so, yeah, I set out to try to find a theoretical home. One thing that was extremely important to me was that I didn't want to do theory that was super far removed from experiment. I really wanted to continue, collaborating with experimentalists and getting involved in experiments, but not necessarily doing them myself. And so, I landed in a group. This is David Masiella's group. It's actually in the chemistry department at University of Washington. And this is a fairly interdisciplinary group that works on all sorts of things, but it sort of homes physicists, material scientists, chemists, sort of across the board. And there I was able to sort of carve out my own path within this group, thinking about nanophotonics theory, cavity QED, some quantum simulation, really lots of different topics. And I would say the general theme for my research was, working closely with experimentalists. So all of these pictures here, these correspond to different experimental collaborations, and trying to build simple models to explain what they're seeing in their experiment. And one of my big takeaways from my work and sort of the theme of my thesis is that Really, these toy models, which oftentimes you can still rigorously derive from sort of the actual physical systems, there's a ton to learn just from simple toy models, in that it can really explain pretty complex physics. And just having good knowledge of say coupled oscillators can give you lots of intuition for different experimental platforms. Okay, and this now brings me to my current position, where, yeah, towards the end of my graduate school career, I started, I was working more and more on quantum simulation, decided I wanted to go back towards quantum computing, and this sort of brings me to where I am now. Okay, so back to the research component of the talk. Let's first dive into what the AKLT model is, and what the AKLT state is, and why we might want to prepare it. So the AKLT model is described by the Hamiltonian shown here on this slide. This is a Hamiltonian for a spin chain, and in particular spin 1 with spin 1 sites. So these are spin 1 operators here. And to construct the ground state of this Hamiltonian, it turns out it suffices to analyze pairs of spin 1 sites. And through combination of both of these terms, and important here specifically this prefactor of 1/3, you can show that if you have a pair of spin 1s, that if you put them in the total spin 0 or total spin 1 configuration, they contribute a minimal and degenerate amount of energy, whereas there's some gap associated with going up to total spin 2. And so what this means is, to construct the ground state of this Hamiltonian, all we have to do is take every single neighboring pair of spin 1s and force it into the total spin 0 or total spin 1 configuration. Okay, so how do you actually do this? This was sort of one of the great insights of Affleck, Kennedy, Lieb, and Tasaki, for who the AKLT model is named. But the basic idea is you take these spin 1 sites and you decompose them into pairs of virtual spin 1/2 degrees of freedom. Then at this level, it's actually quite easy to satisfy this constraint I outlined. All we have to do is take intersite pairs of spin 1/2s and prepare them into the antisymmetric singlet state, which is defined here. And then to recover sort of the effective spin 1 degrees of freedom, we then project intersite pairs into the symmetric triplet subspace. And so I'm also going to introduce some notation, which I'll use throughout this talk, plus, 0, and minus. You can think about these as sort of the 3 spin 1 states in the SZ basis, with eigenvalue +1, 0, and -1. And in the virtual spin 1/2 representation, they take the form of these symmetric states here. Okay, and so what results from this very simple procedure, this is what's known as the AKLT state, and it's indeed the exact ground state of this Hamiltonian, which haven't really proven to you, but just sort of argued. Okay, so much of this has been known for quite some time. Why is it still interesting to think about the AKLT state now? So I'm going to give a few different reasons for this. The first is that the AKLT state provides this sort of historically important and prototypical example of what's known as a matrix product state, or more generally, tensor network state. If you haven't heard of matrix product states, the general idea is the following. So imagine, again, we have some spin 1 chain. Then any state living on this chain, you can describe in the following way, where sitting out front, we have some rank n tensor that encodes 3 to the n complex coefficients, right? So this is true for any general state. It turns out, however, for many states of interest, there's a lot more structure that we can take advantage of in order to compress this information. And this is particularly true for area law entangled states, or ground states of gapped Hamiltonians with local interactions, which is what the AKLT state is. But the basic idea, let's just kind of go through it slowly, is first, let's imagine we just have the singlet state. You can write it in the following way, but you can also sort of factor out this left qubit and this right qubit off to the left and the right, and describe it in terms of this matrix of coefficients S. Okay, so the singlet I can write in the following form, where this matrix encodes these coefficients. You can play the same exact game with the triplet. So now there's 3 different matrices and an additional index here, M. So this corresponds to the 3 different triplet states, minus, 0, and plus. But nonetheless, you can still write down these matrices for these triplet states. So now returning to the AKLT state, we can notice that it has this structure of sort of alternation between triplet, singlet, and so on and so forth. And so taking advantage of that, you can show that this rank n tensor for the AKLT state can be reparameterized in terms of these little 2x2 matrices. So basically, you can express this rank n tensor now as just the product of all of these matrices. There's one for each site. And here, L and R, these are boundary conditions, the left and right boundary condition, which correspond to the state of this left spin 1/2 and this right spin 1/2. Okay, and so this is what's known as a matrix product state with bond or virtual dimension 2. 2 here, this corresponds to either the dimensionality of these matrices, these are 2x2 matrices, or equivalently the dimensionality of the underlying virtual spin 1/2 degrees of freedom, and physical dimension 3. And you can see that this is, of course, a big win over storing these 3 to the n complex coefficients, because all I need to do now is remember these 2x2 matrices, and I can write down the state exactly. Okay, and this is, of course, something that's much more general beyond just the AKLT state. And just because it's going to come back later and be this matrix product state representation is going to be super important for the algorithm, which I'll outline, I want to at least quickly flash what these matrices look like for the AKLT state. So A here, which I should have mentioned, this is a product of a triplet and a singlet. Each of these A matrices, there's 3 of them again, correspond to a poly operator, sigma plus, sigma minus, or sigma z, up to some coefficient. Okay. The other thing I want to highlight is that the AKLT state is also sort of this prototypical example of what's known as a symmetry-protected topological phase. So what this means is that you cannot prepare the AKLT state or any other state in what's known as the Haldane phase from a product state or any other state in the trivial phase through merely local unitary transformations in a finite amount of time, as long as those local unitary transformations obey some protecting symmetry, they preserve some symmetry. So if you break the symmetry, you can prepare it, but if you don't break the symmetry, you can't prepare it in a finite amount of time. So for the Haldane phase, including the AKLT state, its protecting symmetries are spatial inversion symmetry, there's a time reversal symmetry, and also a Z2 cross Z2 or dihedral symmetry. What this means is you take every spin 1 and rotate it by pi about either the x, y, or z axis, and this is also a symmetry. And there's lots of very interesting features displayed in the AKLT state, which you can understand through this lens of its SBT order. So for example, it displays edge excitations. So to explain this, I'll just first state that for open boundary conditions, this Hamiltonian that I wrote down before, its ground state space ends up being 4-fold degenerate. And the way you can understand this in terms of this simple cartoon is that these edge spin 1/2 are unpaired. I didn't pair them into the singlet with anything. And so what that means is they're free to rotate and be in whatever state they want, and you remain in this ground state subspace. So we say it has fractionalized spin 1/2 excitations at the edges. And this is, of course, very interesting because, again, this is a spin 1 model. So all of the physical degrees of freedom are spin 1, yet in the ground state subspace, you have these edge spin 1/2 degrees of freedom. The other thing that I'd like to highlight is that it displays what we call string order. So this is generic for an SBT phase. The basic idea is that if you measure, for example, the spin-spin correlator along the chain, so you measure every site in the SZ basis, what you'll find is that these correlations exponentially decay as a function of distance. So seemingly this indicates that there's no long-range structure in this state. However, if you look a little bit more closely, you'll see that it displays this sort of hidden topological order. And so to explain this, the basic idea is if you measure SC at every single site, what you'll find is that you get this alternating pattern of pluses and minuses with any number of zeros in between. So it's this sort of anti-paradigmatic ordering that's diluted by the presence of these zeros. So something like this is an allowed configuration, whereas something like this is not allowed because we have 2 pluses back to back. And you can think of the AKLT state as a superposition over all of these possible allowed configurations. And you can quantify the string order in terms of what's known as the string order parameter, which is going to come back a little bit later in order to verify the state when I actually prepare it on a quantum device. But nonetheless, it's defined as the following. It basically looks like the correlator that I wrote down before, but now you have some non-trivial rotations in the bulk. And you can show that in the thermodynamic limit, this string order parameter tends to a value of -4/9. Okay, and the last thing I'll just quickly mention is that the AKLT state has also been shown to be a useful resource for tasks such as measurement-based quantum computation. So apologies if you're not familiar with MBQC. I'm just going to sort of state this result that the 1D AKLT state is a non-universal resource for MBQC in the sense that it only ever encodes a single qubit. But there are interesting schemes for stringing together many 1D AKLT states in order to get a universal resource. The spin 3 halves 2D AKLT state on a honeycomb resource lattice has been shown to be a universal resource for MBQC. I won't talk about this here in this talk, but I'll just sort of mention it if you're interested. And because of all of this and the interesting features, which I previously showed, efforts to realize the AKLT model in the lab have been ongoing for some time. So one of the first experiments was back in 2010 in a photonic platform, but there's also been recent experiments, for example, trapped ions, as well as more of a material science approach in something called nanographene. Okay, so right. So now getting into my own research, what am I interested in? I'm interested in the question of how can we prepare the state on a quantum computer? How can we come up with an algorithm to do this as efficiently as possible? And generically, the problem is that the AKLT state, it has a non-zero correlation length. And what this means is you can't actually prepare it with a constant depth circuit that's composed just of local unitary gates. And rather, we require a circuit whose depth scales with the size of the system. And the way to see this is that for any sort of constant depth circuit that we write down, any circuit of a particular depth, there's always going to be some light cone. And you're only going to be able to build up correlations within that light cone, and any sort of correlations outside of it, you can't build up. So this is why, you know, the depth of the circuit needs to scale with the size of the state that we're trying to prepare. What we show in our paper, however, is that you can completely evade this no-go limit. And you can do this by using measurements and feed forward. And in particular, what's sort of fascinating about this is that, you know, measurements are of course inherently probabilistic, but what I'll show is that by leveraging the symmetry of the state, we can make this scheme entirely deterministic and prepare the AKLT state with a constant depth circuit. Okay, so this is now what I'll begin to explain. So what I'd like to do is first explain how you can prepare the state with just local unitary gates, as this is going to give some intuition and really form the backbone for this measurement-assisted approach, which I'll then explain afterwards. So yeah, to explain this, what we're going to do is first remind ourselves this matrix product state form of the AKLT state. Again, a lot of this really hinges on this matrix product state representation, and the algorithm which I'm about to outline for the sequential preparation. This more or less you can figure out something analogous to this for any matrix product state. But the basic idea is we're going to take a cue from this virtual spin 1/2 degree of freedom representation and take pairs of qubits here colored in gray to represent eventually individual spin 1 sites. So these are what I'll call site qubits. And what I'll also do is cleave off at the start one qubit here colored green. I'll refer to this as a memory qubit, and its role is really going to be to assist in the sort of preparation and propagation of correlations amongst the chain. But the basic idea is we're going to start the memory qubit in some state psi naught and all other pairs of qubits in some state 0. So this is the spin 1 0 state. And then what we're going to do is just apply this unitary. The bulk of the algorithm is just going to be applying this unitary, which I'm just going to write down and explain where this comes from in a little bit. But the basic idea is this is a 3-qubit unitary, which has a few different terms. But each term, it has some poly operator, which acts on the memory qubit, and some spin operator, which acts on a pair of qubits belonging to a spin 1 site. And then there's additionally some unitary completion, which we don't particularly care what this is. And we actually have some freedom in choosing it because we know it's just going to give 0 for these input states here. But the basic idea is we're just going to sequentially apply this unitary to all sites. And so I'm just going to tell you what happens when we do this and then take a step back and try to explain. So basically what this unitary will do, will first act on this memory qubit and this pair of sites, and it's going to prepare the triplet. And then it's going to continue preparing the triplet at each site, but also forming these singlet bonds with the previous site. And so after applying this unitary n times to all sites, we'll then end up with a state that looks like the following, where basically we have something that looks quite a bit like the AKLT state, but with this left memory qubit here entangled with this left boundary condition here. Okay, and this is going to be something that's super, super important for getting this measurement-assisted approach to work in a bit. So I'll come back to this in a bit. But first, where did this unitary come from? Why is this doing what I said it done? There's a couple of interpretations. The first is that this memory qubit is just merely enforcing this hidden topological order. And so what I mean by this is if we look, for example, at this first term here, you'll see that we have this poly operator sigma plus, and tied to that is the creation of a plus state with this S plus operator. And because acting with this poly operator twice in a row necessarily gives 0, what that means is we can't actually create another plus until we've flipped the memory qubit and created a minus. And so there's this back and forth between plus and minus, and all the while we can always create zeros with this last term here. And so you can see that what this unitary is doing is it's creating a superposition over all of these configurations which obey this hidden topological order rule, which I laid out. Okay, there's another interpretation, which is perhaps a little bit more satisfying and more generalizable to other matrix product states, in that you'll note that each of these operators here acting on the memory qubit, these are just exactly the 3 matrices which go into the MPS representation, which I laid out before. And you can see tied to this is the appropriate action on the spin 1 site to prepare that particular state belonging to that matrix. And so we can write this unitary in the following form. And now you can see that what we're actually doing is by applying this unitary sequentially, we're accumulating these matrices A on the memory qubit. And you can, through a little bit of math here, sort of mess with this and put it into the following form, where at the right-hand side here, I've made a slight redefinition over here in terms of the singlet matrix. And on the left boundary here, I've inserted the resolution of identity. So what you can see now that this is exactly the matrix product state with the right boundary condition determined by the initial state of the memory qubit, and the left boundary condition is entangled with the final state of the memory qubit here labeled I. Okay, and so this is something that's super important that I want to dwell on for a little bit, and just to sort of foreshadow, what I can do is now make a measurement of this memory qubit to collapse the state onto particular boundary conditions. Okay, and this is going to be really, really important for this measurement-assisted approach in a bit. The fact that by measuring the memory qubit, I can enforce boundary conditions. Okay, and just to sort of generalize what I just showed you just a bit, this is actually the sequential preparation we came up with for the paper, which is a bit more efficient in that here, rather than just using one memory qubit, I'm actually using a pair of them, and I'm using them sort of in parallel to grow the AKLT state in both directions. Okay, so this is a slight speed up over what I just showed you, but just by a factor of 2. And in case you're interested, one thing I actually should highlight here too is at the end, now each of these memory qubits is entangled with either the right boundary condition or the left boundary condition. So this is also going to be pretty important on the next slide. And in case you're interested, what does this unitary actually look like? How complicated is it? You can decompose it into the following circuit, where you could see it's not too bad, just some controlled rotations and C naughts. And one thing I want to highlight here is that this memory qubit, it comes in on the upper wire and comes out on this bottom wire. And so you can see there's some swapping built into this, which is fairly important and is indicated over here. And this allows us basically to run the circuit just with linear connectivity between all of our qubits. Okay, so at the end of the day, this gives us a way to prepare the AKLT state, but in a time which scales linearly with the number of sites. And so the question is, can we do better this? And I've, of course, alluded to the answer several times now. It is yes, by, again, leveraging measurements and symmetry. So what's the idea here? So we're going to need 2 different ingredients. The first is that we can basically prepare separate little matrix product states and fuse them together with measurement. So the basic idea is if we have 2 little AKLT chains, and we now make a measurement that entangles these 2 memory qubits, say we measure it in the Bell basis, then what that's going to do is prepare the following state, where now we have some Bell pair here, which is of course probabilistic, And paired with that is something that almost looks like the AKLT state, but with some random bond thrown in here. So we characterize this in terms of the matrix product state representation in terms of this defect matrix B. And this defect can take the form of any one of these 4 Pauli operators corresponding to the 4 different Bell measurements. Okay, so this is the first ingredient, and I'll just say that this generically will work for any matrix product state. Okay, but this is of course probabilistic. And so the other ingredient is that we can actually make it deterministic by leveraging the symmetry of the state. So the basic idea, and apologies if you haven't seen these sorts of diagrams, I'll try to explain what's going on here. But the core principle is that this block A, this box here, these are the matrices, rather the tensor that builds up this matrix product state representation. And what this diagram is saying is that if we take these matrices and we conjugate by any Pauli operator B, then by Z2 cross Z2 symmetry, this is exactly equivalent to acting with some unitary on the spin 1 site. And so the idea here is we don't really have access to these virtual spin 1/2 degrees of freedom, so we can't remove this operator. However, by acting with some unitary on the spin 1 site, we can actually move around these defects on the virtual level. So that's the basic idea. And this is any symmetry protected topological phase is going to have some sort of symmetry like this. And so we're really taking advantage of the SPT order of the AKLT state here and its manifestation at the level of these local tensors. But practically what we do is now, we know what our measurement result was, and we can take this information. This is where feed forward comes from. We can take this information and now just apply, say, this unitary here, which is going to slide this defect over to the left. And then we can apply it again to slide the defect over further, and finally act with this operator B at the left edge to remove it entirely. And so in this way, we've now prepared the AKLT state deterministically, despite our use of probabilistic measurements. Okay, now we can put these ingredients together to outline the full constant depth preparation. What this looks like is pretty much we're just going to prepare lots of little AKLT states. So we first entangle the memory qubits by preparing them into the singlet state, and then apply just a single layer of these unitary gates to prepare little AKLT chains. Then the key step is to apply what we're calling fusion measurements. So here again, these are the Bell measurements between pairs of memory qubits belonging to different chains. And everywhere we measure the anti-symmetric singlet state, this is a successful fusion and yields a longer AKLT chain. However, measurements are of course inherently probabilistic. And so everywhere we get some other results, we now have some defect living in our state. And then using feed forward and using knowledge of what defects you have, you can always leverage symmetry now to apply just a single layer of these unitary gates to remove the defect entirely and result in the AKLT state. Okay, so this now gives us a way to prepare the AKLT state in constant depth entirely deterministically, or in other words, in a time which is constant in the size of the state. I'll just mention that this not only beats out the sequential unitary approach, which I showed previously, but also several other recent proposals which have been published in order to try to prepare the AKLT state. So both this adiabatic and dissipative approach involve times which are polylogarithmic in n. And this is really, I want to emphasize, a huge win, because a constant depth circuit is super helpful, for example, in the NISQ-era, where we're limited to fairly shallow circuits. So what this means is this allows us to prepare larger states than we would otherwise be able to. Okay, so I'll now sort of go towards the, let's see, I have maybe 10 minutes, so we'll see how much of this I can get to, but I want to give some quick highlights of some of the experiments we ran on an IBM Quantum processor to really show that this measurement-assisted approach can outperform its sequential unitary counterpart. And so just kind of quickly outlining what we did is we used the 27-qubit device, IBM Hanoi, and prepared the state around the circumference of this qubit graph. And this allows us to prepare up to a 6-site AKLT chain, but again, 6 spin-1 sites, so really composed of 12 qubits. And then there's additional overhead due to the memory qubit. So it's really like an 18-qubit experiment. And we use some particular encoding where, maybe I'll just skip over this because of time, but it has some nice properties, which we take advantage of. And what the circuit looks like that we run is what's shown on the right-hand side here. So again, we prepare the singlet, apply this unitary, make a transformation to the Bell basis, and then, of course, do our fusion measurements at the end. So these pairs of measurements here, these correspond to the fusion, whereas these edge measurements, this is the measurement of the edge memory qubits, which collapses onto particular boundary conditions. Okay, so you'll note that there's a step missing here. I'm not using feed forward and correcting the defects on the actual device. And this is really because at the time of running these experiments, this wasn't a feature that was yet available to the public on IBM Quantum processors, but it actually now is. So we could go back and run this. However, we sort of used a trick in that all of these defects, it turns out, can be corrected in post-processing. And to explain the basic idea is, say we have an X defect, then this is removed with the following unitary operator, which you can see all this does is permute the spin 1 encoding, basically the spin 1 basis states. So if we just keep track of where our defects are, then all we need to do is change the local encoding for our spin 1 sites, and that will correct the defect. Okay, so that's the technique that we use, and we compare this preparation with this measurement-assisted approach to the sequential unitary approach, which you can see is a much deeper circuit. Okay, and so I'll start just by quickly flashing some results for a couple of the ways we actually verify the state. So we measure both the string order parameter as well as the entanglement spectrum. And if there's time, maybe I won't explain exactly how it works, but I'll also flash the results for quantum teleportation. So here the idea is, after preparing the state, you can use it as a quantum wire to teleport a qubit from one end to the other. Okay, so starting with the string order parameter, again, defined on the left-hand side here. What I'm showing on the right-hand side is the string order measured edge to edge for chains of varying chain length. So from length 2 chains all the way up to length 6. And there's 2 different plots here because we're splitting into different boundary conditions. The reason for this is, in the thermodynamic limit, you expect the string order to go to -4/9. However, there are finite size effects, and these finite size effects impact different boundary conditions differently. So there's 2 different classes that we post-select on here: symmetric boundary conditions and asymmetric boundary conditions. But you can see across the board, comparing theoretical expectation, this dashed curve, with sequential and measurement data, measurement-assisted results, you can see that the latter is really outperforming the former, even for the relatively small system sizes studied here. And this is something we find across the board in all of our experiments. And we can dig a little bit deeper into this, and to explain this, it's a little bit technical, but the basic idea is, say we have a length 6 chain, which is what I'm showing here on the right-hand side. You can measure the strings of any particular length, length 4, length 5, length 6, and also at different locations along the chain. And so it turns out, particularly for the AKLT point, when you do this, theoretically, you expect to find the same number every single time. So that's what this is testing here. This dashed curve, again, is the theoretical expectation. And what I'm doing is measuring longer and longer string lengths. I'm also measuring in different spots. That's what these smaller markers are here, but you can just focus on the big bold markers, which are the average. And you can see, as we measure longer and longer strings, for the sequential preparation, we find this sort of exponential decay of the string correlations, whereas for the measurement-assisted approach, we find that we don't see this behavior as obviously. So this is sort of evidence, again, that having this constant depth circuit in preparing the state with measurements really is preparing the state much more reliably. Okay, then let me just flash some results for the entanglement spectrum. So the basic idea here is okay, so first, what is the entanglement spectrum? So the classic way to sort of probe the entanglement between subsystem B and subsystem A is to compute something like the entanglement entropy. And the way you do that is you first compute the reduced density matrix for subsystem B, and you can find its eigenvalues and compute the entropy, which is a function of those eigenvalues. What the spectrum refers to are just the eigenvalues themselves, or more technically, it's the negative of the log of the eigenvalues, but nonetheless, the reason this is interesting to look at is because it really provides a bit more information than the entanglement entropy. In particular, for SPT order, it's expected that you'll always find a degeneracy in the entanglement spectrum. So we set out to see if we could actually observe this on an IBM device. And how we actually measure the entanglement spectrum is, again, a little bit technical, but the basic idea is, say we've prepared this chain up top, then we know through the sequential unitary preparation that we could use this memory qubit to continue preparing all of the sites off to the right. And so what that means is the entanglement between this memory qubit and all the sites to the left, it must be identical to the entanglement between all the sites to the left in this situation in sort of these fictitiously prepared sites off to the right. Okay, so long story short, we can probe the entanglement in fairly large chains by doing tomography on the memory qubit and extracting its eigenvalues. And so one obvious question which immediately arises is, isn't there a huge dimension mismatch here? I'm telling you that the eigenvalues of this density matrix are equivalent to the eigenvalues of this density matrix, which could have, who knows how many spin one sites and even an infinite number. The reason that this is not a problem is because, again, this is a matrix product state of bond dimension 2, and the bond dimension sets the maximum Schmidt rank. So it turns out all we need here is a qubit in order to characterize the entanglement in the AKLT state. Okay, so long story short, this is what we do. There's one more technical detail which I have to touch on is, I'm telling you we expect to find some degeneracy in the entanglement spectrum. What that would mean is finding this memory qubit in the maximally mixed state. However, if I measure that on a noisy device, who's to say this qubit just hasn't completely decohered? Is it really evidence of entanglement in the prepared state? And so in order to deal with this, what we do is we instead probe finite size effects in the chain. And in short, we can measure the left memory qubit, and then conditioned on the outcome of that measurement, we then do tomography on the right memory qubit and extract its eigenvalues. And theoretically, when you do this, what you expect to find is that the eigenvalues trend towards degeneracy, but following this exponential curve, which has a length scale, which is equivalent to the coherence length of the AKLT state, which is this known number here. Okay. So what do we see in experiment? We see the following, again, comparing measurement-assisted and sequential preparation and comparing to theory. We find that the measurement-assisted approach is outperforming the unitary approach. And maybe I'll just focus on the measurement-assisted now. That's sort of the last I'll say about the sequential unitary approach. But we can also fit this exponential curve to the measurement-assisted data and extract out an estimate for the coherence length. And so this is one way we test how well we're actually preparing the state. And the number that comes out when we do it for this particular data set is the following. And so you can see this is within 1% of the theoretically expected value, which is really, I think, terrific agreement, particularly on a noisy device. It wasn't just